Right, so 6.3 and 6.4, we've already learned about exponential functions. So now we're going to have the opportunity to learn about the inverses of exponentials, aka our logarithmic functions, and then we'll also learn how to graph logarithmic functions. Maybe I'll give you a foreshadowing. I screenshotted some cool exponential and log functions before. Can insert in the other ones later, but we already learned about the blue. Now we're going to be learning about the red. Inverses, what do we know about inverses? Swapping your x and y values. Oh, what's this green dashed line? Y is equal to x. All of your x's and y's are flipped. Okay, reflecting across your line of y equals x. So what are our learning objectives here? We have a lot. We are going to be able to convert between log and exponential form, which I find to be probably one of the most important topics that you'll learn about today. The evaluating expressions is pretty straightforward. I would say that's probably the easiest of the objectives. We'll be able to use common and natural logarithms. That's just notation that I verbally spoke about, but we'll just get more exposure with. And then finding domain and range, you're quite familiar with this. It's just now we're going to look at it from a logarithmic standpoint. And then last but not least, we're putting all of that together so that we can properly graph log functions and transformations of those log parent functions. So before we jump into some examples, we have some definitions. And I know I've said this a few times now, but again, logarithmic functions are just inverses of our exponential function. Exponential functions, what do we know about their properties? Just to recap from our previous lesson, they're one-to-one functions. We need that b value to be positive. If the whole function itself is negated, then that's where that reflection across your x-axis occurs. And then in order to find your inverse of this function, how do we find inverse? We flip our x and y values. And so our inverse is represented here, which is known as our logarithmic function. Now jumping into our definition of our log function, we can represent this form right here of our logarithmic function is known as our exponential form. But we can also write that as our logarithmic form, which is what we have down over here. And so that's why it's actually very important to know the vocabulary in this section, because you'll always hear the word base be thrown around from an exponential form standpoint, as well as from the logarithmic form standpoint. So if we take a look at the exponential form, we have x is equal to b to the y. Y represents our exponent, b represents our base. And then if we switch over to our logarithmic form, we have y times log base b of x. That base b is the same as the base b in that exponential form. And then last but not least, when referring to the domain, think about back to inverses of regular functions and the relationships between domain and range. It's flipped, right? If you have a function f of x is equal to x plus 5, and I mean, that's a linear function, so you know your domain's going to be all real numbers. But let's say you have a random function, your domain is 1 to 5, and your range is all real numbers. Now you want to find the inverse of that random function. Well, now your domain is all real numbers and your range is 1 to 5. Your domain and range flip when it comes to inverses. The same rule applies over here. You know that in exponential functions, you have no restrictions for your domain. It's all real numbers. But when you're looking at the inverse, the logarithmic function, you do have the restrictions on the domain. You do not have the restrictions on your range. So it's just opposite. And this is a more less wordy slide highlighting the same thing that we just previously spoke about, the differences between your logarithmic form and your exponential form. You have your exponent here, which is represented as your solution for the log form. You have your base, and then you have your x values. So we finally arrive at our first example, where we just want to become more familiar with converting from logarithmic form into exponential form. I always like to use arrows here because, again, log base 6, that's like 6 raised to your exponent, is equal to the square root of 6, sort of like a circular motion. Yeah. So back to this question, we have in exponential form, 6 raised to the 1/2 is equal to the square root of 6. And that checks out, right? Okay. Let's look at part B. 3 raised to the 2nd power is equal to 9. I always have the famous example stuck in my head. If I ever get confused, I'll write it off to the side here. I know that 10 squared equals 100. And log without any base is really known as our common log, which has a base of 10. So you can also write it as log base 10. And so when we look back at the 10 to the 2nd is equal to 100, this is just log of 100 equals 2, also known as log base 10 of 100 equals 2, aka 10 to the 2nd power equals 100, coming full circle.
So the base is going to be the biggest number, the rest is going to be the exponent, and the number inside the parentheses is going to be the rest.
Yeah, exactly. You got it. Nice. So let's look at some more examples, but now we're given the exponential form and we want to put it into logarithmic form. So part A, 2 to the third equals 8. Our base is 2, log base 2 of what 2 to the third gives you 8. Let's look at part B. We have 10 to the negative 4 equals 1 over 10,000. What's your base? Log base 10 of, or to the negative 4 gives you 1 over 10,000. Yeah. You don't have to, especially if you write this small enough. It's just to help separate, to really visually see it. Yeah. How did you guys feel on this scale of 1 to 5? Say that again. You're always gonna have a base. Yeah. You're just, again, common log, the base isn't visually shown, but it's there. So common log base 10, you would have log 1 over 10,000 equals negative 4, but these both mean the same exact thing. Yeah, anytime there's no base, it's because your base is 10. Yeah, yeah. Anytime there's no base represented, your base is always 10 in those examples. Yeah. So common log base equals 10. So if you see a question and there's no little exponent on the bottom, then you know automatically it's base 10. Okay. Our second objective is being able to evaluate log expressions. And this is where interchanging between exponential form and log form is helpful because then you can compute those famous numbers. And so they start off with our straightforward log base 2 of 8. And so what is this saying? Okay, well, 2 to what power gives you 8? Wow, 2 to the third, which means log base 2 of 8 is 3. And that's essentially what they're saying down here. To what exponent must 2 be raised in order to get 8? So now knowing that, let's practice with our example 3. Log base 4 of 64, 4 to what power gives you 64? Right, 4 to the y gives you 64. Well, we know 4 to the second is 16. About 4 to the third. What's 16 times 4? Yeah. 4 to the third is 64, right? So we get y is equal to 3. Do another example. We have log base 3 of 1 over 27. So 3 to what power gives you 1 over 27? Well, 1 over 27 is a fraction, which means you know that this exponent's going to be negative. But what power with that base 3 gives you 27. You know, yeah, exactly, 3. So our answer is -3. And so now this is what I was speaking with Valerie about, and then what I mentioned about the natural logs earlier in the objectives. But any time that there is no little exponent represented, that means we're dealing with that straight common log, and it's just a base of 10. And then the natural logarithm is when we're dealing with a log base e. And another way to represent this notation-wise, not a lot of the time will you see log base e of x. Instead, you'll see ln of x, which stands for natural log. These are synonyms of one another, but you just happen to see that ln of x way more. And if you do end up practicing homework problems with your calculator, ln of x is the notation on calculators as well. So, speaking of calculators, we are asked to evaluate each logarithmic expression using your calculators or Desmos. And so, again, these types of questions you will not see on an assessment because you are taking your assessment calculator free. So I will do the liberty and calculate it for you guys to save some time. So log of 1,000, which actually you could calculate this on your own. That's just 3, right? Yeah. Right, because 10, it's base 10, 10 to what power gives you 1,000? So that first one, it's free game. Second one, not so much. Natural log of 500 is going to be a decimal. Yeah. So again, we're looking at natural log is the same as log base e of 500. So e to what power gives you 500? It's approximately 6.215. Right, now we're on to our fourth objective for today, where we are finding domain and ranges of logarithmic functions. And again, they're the inverses of the exponentials. So when we're dealing with range now, we have no restrictions. It's just now the domain is restricted based off of that vertical asymptote, which we'll later see when we practice graphing. And so down here is just recapping and reviewing what your range and domains would be for our general functions when we're dealing with exponentials, and then what our range and domain will be for general logarithmic functions, how the range and domain is flipped. Also, another thing to point out is the fact that when you find the domain after transformations occur, it will vary. Just like we did when we were dealing with exponential functions, when we applied transformations, that range varied with the horizontal asymptote changing. So it's important to remember also that the domain only consists of positive real numbers. So now we're going to practice this in our example 6, where we're given our logarithmic function f of x is equal to log base 2 of x plus 3. So we have a horizontal shift taking place, and we want to find the domain and write our answer using interval notation. So let's maybe look at this graphically first. And we'll put in the parent function as well. I want to see if we have just a log base 2 of x already graphed out. I think we do, yeah, right here. Saves us some time. So the red is the parent function, our log base 2 of x, which again is just a reflection of our 2 to the x across our line y equals x. But this plus 3 is going to represent what? What type of shift? Horizontal shift. How many units and in what direction? 3 to the left, exactly. So good rule of thumb is you want to find a good point. So why don't we do our 1, 0 here? We know that that falls on log base 2 of x, which means if we're doing a horizontal shift 3 units to the left, now we're looking at this being our new point. And then we can maybe do one more, right? Our 4, 2, move 3 units. I think everything else will just stay as is. Another one that we should move over, because right now we have this vertical asymptote at x equals 0. When we have that horizontal shift take place, that vertical asymptote is now shifting 3 units as well. So now where is our new vertical asymptote? At x is equal to what? Zero minus 3 gives you what? -3. So x equals -3 is our new horizontal asymptote. I'm saying horizontal, it's vertical. New vertical asymptote at x is equal to -3. So now from there, we can very easily sketch out our log function. And then I'll label it f of x equals log base 2 of x plus 3. Does everyone see that? And so last but not least, what's our domain here? What are all of our possible x values? It'll never hit -3. So we're going to have a soft bracket there. And then what about our highest x value? Yeah. So what do we notice? Just like in exponential functions, our vertical shift represented our range, and our horizontal asymptote, Well, our horizontal shift with logarithmic functions represents our domain and our vertical asymptotes. So a lot of patterns when it comes to mathematics. Yeah.
Log to X. For
Very, very good question. If you didn't have this, you know that any log function is going to be in this sort of shape. But let's say you didn't have this at all, just go straight back to choosing good table values. So if you had none of this, then I would say I would do negative, what makes this one? -2? Because 2 to the what power gives you 1, that gives you 0. That's a very famous point. And then if we have x is 1, 2 to what power gives you 4? That's just 2. Should probably have that in the other direction. And then if we plug in 0, 2 to what power, that would give you a rough number. I think those are probably the best numbers. You could also do 8, right? 2 to the third gives you 8. So x is 5, and y is 3. And so if x is 5, y is 3. 1, 2, 3. Kind of drew this a little bit off, but yeah. So definitely just do tables.
is it okay if um log to the X and then negative
Switch the y to the exponential form and then when you say put the negatives on the y, for graphing, you're saying, or for computing the table values? Table values, yes. If you're just looking at the function to graph, oh, okay, I know what you're saying. You're saying put it into exponential form, and then it's like you're utilizing pretty much transformations of, yeah, 100%. Definitely do that. Yeah, that's a great way to look at it. All right, let's do another one. So these, we didn't even have to graph it. I think I just graphed this for you guys to visually see. But now that we have a good understanding of it, we really don't have to. So we're just asked to find the domain here, and we're given our function f of x is equal to log. I'm gonna put the -2x first so that you can really see that horizontal shift that's taking place, right? We have a horizontal shift of 5 units to the left. And so this tells us that a horizontal asymptote is what? Keep saying horizontal asymptote. It's vertical asymptote. X is equal to yes. Good. And so then what is our domain? We have, it's not negative infinity to -5. Wait. Yeah, it is because it's negated. Good. Negative infinity to -5. And then including -5 or not? No. Good. So, I did forget about this -2 over here, which does affect the horizontal shift slightly. We are shifting 5/2 units to the left. Maybe I'll use a black pen so you could really see it. And so because our C value, aka our horizontal shift, is -5, then we have our -5 divided by this coefficient in front of our x to give us our vertical asymptote, which once again is the same as our horizontal shift. So that's why it's not a -5 for our horizontal asymptote, it's 5/2. Which means our domain is -infinity up to 5/2. And you can write this as positive 2.5 as well. That may make it easier if you have to graph it out. But so, yeah. And I'll write it the other way as a mixed fraction as well. I also want to quickly show you a very easy way to calculate domains when you're dealing with log functions. You know that your basic log function, log of x, your domain is from 0 to infinity, not including not including 0, since that's a vertical asymptote. So when you're calculating this in terms of 5 minus 2x now instead of just x, you know that that needs to be greater than 0. And so now just utilize your inverse operations, add 2x to both sides, and you get 2x is less than 5. And then last but not least, divide both sides by 2 so that you get x is less than, or just less than 5/2. And so that's your domain, which checks out -infinity up into 5/2, not including 5/2. So two different ways to go about analyzing domain. The algebraic way is definitely a lot more efficient, but it's good to understand it from the visual standpoint, utilizing your knowledge of transformations as well. Now we're going to look at example 8, where we're now dealing with natural logs. Again, natural logs is just log base e. And so our function f of x here is 4 minus x squared. And we want to find the domain or the domain using interval notation. So again, because we're dealing with the natural log, I'm going to sketch it out. I'll use the same graph as before. this one. And I'm also going to put that negative x squared first. So you can see that horizontal shift. This one, I think it's best to just create a table of values and choose some good values. So let's see. Let's definitely do 0. And then we have the natural log of 4 is going to be your y value, which will compute the decimal of that in a moment. And then let's do, we can do 1. I guess none of the negatives really matter because it'll just shoot up again. We should really get in 2. Yeah, we're good. And then maybe 3. Okay. So we have -1 plus 4 gives you a natural log of 3. Then we have negative ln of 0 here is actually undefined. Can we get a 1 here somehow or no? Because ln of 1 is 0. This would have to be -3. So if we did the square root of 3 squared, yeah, let's get that one in. Square root of 3 is like 1.7, right? Yeah. So we have square root of 3 squared, which gives you 3. And then we have that -3 plus 4 gives you 1. Natural log of 1, again, is the same as e to what power gives you 1. Anything to the 0 power gives you 1. So square root of 3 and 0, that's a famous one. And then if we plugged in 1, then we would get natural log of 3. That's how, same values. And then 2 should also be undefined, which means we're going to have a nice vertical asymptote. And then 3 is going to be also undefined, right? Can't take the natural log of negative numbers. Okay, so now when we plot this, natural log of 3 as a decimal is about 1.1. And then the natural log of 4 is about 1.39. Okay. So -1, comma 1.1. 0, comma 1.39. And then 1, comma 1.1. And then square root of 3, comma 0. Okay. Now we want to put in our vertical asymptote. And so where's our vertical asymptote? And then we can, let's see. I feel like we have some more. Yeah, so our slight mistake was 4 isn't the horizontal shift because once again, like that needs to be with our x. So what you want to do here, especially we have that exponent of 2, we can factor this. So we get 2 plus x in parentheses, 2 minus x. And then you can use these to determine what your vertical asymptote is, which you kind of saw over here on the table that we did together at 2 and -2. And so we're going to move this guy over. To over here, and then we'll be able to sketch it out. Yeah, we want to be on the lookout for if there's an exponent associated to your variable or not, because then that changes your asymptote. Also, 4 minus x squared, even though it's a natural log function, we have that x squared, which really changes the shape of this a bit. And it ends up being, notice how we had a little dip going on? It ends up being like this is our max point at our y-intercept. And then we have these vertical asymptotes taking place. So what we have in purple represents our sketch of the graph. Yeah. And then in terms of our domain of the function, our domain is all values wedged between these two vertical asymptotes, which means it's from -2 to 2. And what's the reasoning behind that? Well, again, you cannot take the natural log of a negative value. It's impossible. So did you have to solve this graphically? No, you didn't. They didn't ask you to, but I kind of wanted you to see the visual. If you come across this question and you're just asked to find the domain, the easiest way to go about it, and maybe I'll go on the next slide to show you. So ln of 4 minus x squared, just gonna remember that. We want to make sure in these parentheses has to be greater than 0. So 4 minus x squared is greater than 0 to find domain. And then from there, then you just, again, go back into 4 minus x squared is the same as 2 minus x and 2 plus x. All right, well, what does that tell us? We have a great or, and then we have our critical points at -2 and positive 2. And then we just test our values. And you'll notice that we get negative results if we choose a value that is smaller than negative 2 or greater, right? 4 minus 100 gives you a negative number. 4 minus, in parentheses, negative 10 squared, which is also 4 minus 100, negative. So those are bad. The only positive results you'll get are between these two numbers, which will then tell us that our domain is all numbers between negative 2 and positive 2. Yeah. On a test, you would not be expected to graph a function like this. But finding a domain of a function like this, dealing with a higher degree exponent, is free game. The key is to just set what's in parentheses to greater than or equal to 0, and then just go from there. Yeah. Not, well, actually, with greater than 0, yeah, yeah. And if you're ever hesitant about it, then just test your values and you can see between which interval is it positive or negative, and you want to find only the positive ones. Yeah. Any other questions? Trying to see how you're doing on time. Yeah, we're good. Cool. All right. Let's keep going. So now we're finally on to graphing logarithmic functions, even though we've done it a few times already. And yeah, I would say when it comes to graphing either exponential or logarithmic functions, it's always good to know one of the famous ones. So log base 2 of x, or even just log of x, and then utilizing your transformations from there. These are just our characteristics of our log base b of x functions. Again, it's a one-to-one function. Your range has no limit. Your domain is the one that's restricted here based off of your vertical asymptotes and those transformations that take place. Your x-intercept we have as 1, 0, but that does change if you're dealing with transformations. Y-intercept, in this case, there's none because we have that vertical asymptote at x equals 0. But again, that would change if we have a transformation that takes place. And then these last two are just where the function is increasing and decreasing. This is a visual of what our log base b looks like, which you've seen a few times now. So I think we're ready for our example 9, which is just graphing a log base 5 of x. And again, I'll just use that same photo so you can really see the comparisons between, maybe I should use a different one so it's not as bunched up. Do we have another? Let's use, I'll put in this one because then it offers more transformations as well. But then we'll plug in our log base 5 of x. The red one is log base 10 of x. And maybe after we do this question, I'll create another graph for you guys to really hone in on the difference between like log base 10 of x and log base 2 of x and log base 5 of x. How much closer is one to the axes than the other? So your log base 5 of x, 5 to what power gives you 1? 5 to the 0. So let's have our y value be 0, and then our x is 1. It's our famous x-intercept. And then there are no transformations that take place, so we have our vertical asymptote remains the same at our x is equal to 0. Now, what's the relation between log base 10 of x and log base 5 of x? Well, the greater the number is in the base, the closer it's going to be to the axes. I'm really going to accent this a bit more than it needs to be. But with log base 5 of x, I'm making it further away from your x-axis and further away from your y-axis. And then you're done. This should be approaching 0. There. So this is our log base 5 of x. Again, your range in this case has no restrictions now. It's just negative infinity to infinity. But your domain is what? 2. Yeah, exactly. Good. And then we have our asymptote, vertical asymptote at x is equal to 0. And that's it. But I really do want to create another slide just emphasizing the log base 2, 3, 4, 5, 10 of x. So I'll do that really quickly on the next slide. And the same works for exponential functions. When you have a higher base, you're going to be hugging the axes a bit more. So that 1, 0, that x-intercept is going to be where all of these functions hit. And we'll keep the log base 10 of x in here. So that's going to be the one that's closest to the axes. All right. So we have log base 10 of x. And then we'll do a log base 5 of x, which is now slightly further away. From both axes. And then we'll do a log base 2 of x, which is even further away. Notice how all of them are still approaching that asymptote at x equals 0. Notice how at this point, 1 comma 0, it sort of crosses over. It's not like these are the functions. It's like they're crossing over into 1. Okay. Any questions on this? All right. Let's keep going. Previous one. Yeah. Okay. So we're now on our sixth objective. And as we spoke about in the beginning, transformations of log graphs behave very similar to their parent functions. So now we're going to be looking at examples that do involve some shifting and transforming. And so this is just a visual of seeing the horizontal shifts that take place. And again, I know that we initially made that mistake with that whole x squared, but you really just want to be mindful of when you're looking at those horizontal shifts, your x is of the power of 1 so that you can really state, okay, that c value is our horizontal shift within our function. And then these are just, let's see. Yeah, this is just the general formula for a log function that is showing a horizontal shift. That shift of c units. If c is less than 0, then it's going to be shifting to the left. If c is greater than 0, then it's going to be shifting to the right. And then very similar to exponential functions where the vertical shift represented your horizontal asymptote. When it comes to logarithmic functions, your horizontal shift represents your vertical asymptote. So putting all of this together, we want to sketch this log function, which has a horizontal shift now. And then we want to include some key points, include the asymptotes, and then state the domain, range, and asymptote. Right? This one I'm just going to do on a plain graph so you can just really see it. Okay, what is our vertical or what's our horizontal shift? 2 units to the right or left? Which tells us that we have a vertical asymptote or a horizontal asymptote. How many people think vertical? How many people think horizontal? It's vertical, right? Vertical asymptote at what? At x is equal to 2. Yeah. Okay. So let's sketch in our vertical asymptote. And then we'll create some table of values. To put in some key points. Okay. So key points, 3 to the 0. So when y is 0, what is our x? We need this whole thing to be 1, which means x has to be 3. right? 3 to the 0 gives you 1. So that's a key point. Then from there, we can pretty much sketch it out, right? We have log base 3 of x, so this is going to be approaching infinity, and this is going to be approaching 0. And then we want to write out our function. And last but not least, let's state our domain, range, and asymptote. Well, we have the asymptote here. So what's our domain? Nope. Say that again. That's our range. Yeah. Our range is all real numbers or negative infinity to infinity. Our domain is 2 to infinity. And then we're done. Yeah. Good question. I always do the when y is equal to 0, what is this whole thing? And the reason why I do that is so we have log base 3 x minus 2 is equal to 0. Because I know that in exponential form, 3 to the 0 power always gives you 1. So we have 3 to the 0 gives you x minus 2, but we also know 3 to the 0 is 1. So it's a very easy, it's a key point that we can compute without a calculator. Because then we just set x minus 2 equal to 1, and then we solve and we get x is equal to 3. Does that make sense? Any other questions? Yeah, exactly. Yeah. All right. Oh, does it say shift alongside? Oh, no. Yeah, sometimes they'll ask you to graph the parent function too, which is kind of like why I kept putting in that previous graph. Where is it? Right here. I kept putting in these to really see a parent function take place, but I wanted at least one example where it wasn't really cluttered so you can very visually see what's going on. Right. And then this is just a slide really jumping into vertical shifts. And so vertical shifts just move your graph up and down, but it's not going to affect your domain and range. Horizontal shifts do. So when you're looking at your vertical shift, again, it's that plus constant number at the end of your function. That's going to tell you how many units you're moving your function up or down. And again, this is saying that your vertical asymptote is going to stay the same. It's not changing. And your domain and range are also staying the same. So now knowing that, why don't we graph our log base 3 of x plus 2, so a function that has a vertical shift up 2 units. And then I'm going to put in, for this one, I'm going to put in the parent function log base 3 of x. So I'll just very quickly sketch it out here, pronouncing it a bit, but it's okay. Yeah. And so now when you shift this up, we have up to your vertical asymptote is staying put exactly the same. And so now it's just going to be that's it. So let's write off to the side. We have a vertical asymptote at x equals 0. What's our domain here? Yeah, and what's our range? Yeah, and we're done. Questions at all? Neat. Now let's look at reflections. And so very, very similar to everything that we've spoken about before. If there's a negative in front of the entirety of the function, what's going to happen? It's going to be a reflection across the x-axis, right? All of your y values are now being negated. If the negative is attached specifically to that x variable, then it's going to be a reflection across your y-axis. Okay, and so these are just visual examples representing that, right? Negative smack in the front, it's flipping over x, negatives attached to the x, and then it's flipping over your y. And so this is just talking about the properties, the domain and range when that reflection occurs. Again, I wouldn't memorize any of this. If you know the visual, then you know based off of the visual what's going to be happening to the domain and the range. And then I believe this is our, last example for this problem or for this section. We are asked to sketch this graph of log of negative x. And so straight off the bat, what type of reflection is occurring? It's a reflection across. Yeah. Because remember, all of your once positive x values now become negative, and so it's flipping over that y-axis. It's a reflection across your x-axis when the entire function is negative. So reflection across your y-axis. And so from a sketch standpoint, we'll sketch out both. this is just log of x. And then our log of negative x is here. And so key point is that -1, 0 when it's reflected over our y-axis. And then last but not least, let's state our domain. Our domain, and I know Alexandra mentioned this in an earlier example, is now going to be from -∞ to 0. And then our range is unchanged, yeah. Finally, we have, once again, our vertical asymptote at, yeah, x is equal to 0. So that concludes our sections 6.3 and 6.4.